Hello friends, welcome back to your favorite channel Science with Mukherjeesir. Myself KK Mukherjee. Today we are going to discuss a very important topic in chemical kinetics, that is how the reaction rate of the reaction depends on the temperature of the reaction. That is the temperature dependence of the rate of the reaction. So it is video number 8. So we can write. So in this video we are going to discuss the temperature dependence of the rate of reaction. The rate of reaction is very much influenced by the temperature of the reaction. One simple example can clear this. That is the decomposition of N2O5. You can understand that. Decomposition of N2O5, when we decompose N2O5 at 0 degrees Celsius, it takes almost 10 days. It takes almost 10 days to decompose by its half of the original amount. When it is at 25 degrees Celsius, it will take 5 hours to decompose to its half amount of the original. And it is only at 50 degrees Celsius you will find that it decomposes to its half of the original amount by only 10 minutes. So you can understand how important this temperature factor on the rate of reactions. Now question arises, anything is there, anything explained, anything observation is there. This is the observation. Thus N2O5 has been decomposed with a different time to its half by different temperature. And thing is, why it is so? What is the reason behind it? The reason is, that is we going to explore in this video why it is so. So till the end you must see this video, right? It has been observed that 10 degrees Celsius increase of the temperature of the reaction, it will double the rate constant. It will double the rate constant. You can write this. 10 degree increase, double the rate constant. So you can understand now why it is so. When we decompose N2O5 at 0 degrees Celsius, it takes almost 12 days to decompose to its half of the original amount. When it is 25 degrees Celsius, it decomposes in 5 hours only. And when we increase the 50 degrees Celsius, it decomposes in a 10 minutes. So that is basically the rate constant is going to influence by the temperature of the reaction. Right? So there is a terminology, a technical parameter. This is called the temperature coefficient. So what is the temperature coefficient? Temperature coefficient of the reaction, and it is been N, denoted by N. Temperature coefficient of the reaction is basically the ratio of the rate constant. Ratio of the rate constant at 298 Kelvin and at 308 Kelvin. It ranges from 2 to 3. Let us understand this. What do we mean by the 2 to 3? Suppose the temperature coefficient of a reaction is 2. Then what we say? Suppose this is the rate of reaction R and it is having the temperature coefficient 2. Then as 300 Kelvin is of reaction is R, then 310 Kelvin, its rate of reaction will be 2R, and C with the increase with coefficient 2. With coefficient 2, that will be like this. The reaction rate of the reaction is doubled. Means the rate constant is also doubled. That is why rate of reaction is being doubled. 2, that is 4, and that is 8. If it is 3, then this number will change. 3, that will be 9, and that will be 27. So rate constant, you can see when it is 3, coefficient is 3, then rate of the reaction initial suppose R, then will be 3R, then will be 9R, then will be 27R. So this is the crude way of analyzing the rate of reaction, making a correlation between the temperature of the reaction and the rate of the reaction. But it is first given by a scientist, Arrhenius. He has given a quantitative analysis of the relationship between the rate of the reaction and the temperature of the reaction. That we will understand today. Today we will understand on the Arrhenius reactions and its graphical representations. Everything we will understand. Okay? So we can write here the Arrhenius equation. What is the Arrhenius equation? Let us understand. This is the Arrhenius equation. This correlate This is the Arrhenius equation. Here K is the rate constant. You can write K is rate constant. A is the constant and it has various names. It is called P-exponential factor. P-exponential factor, one name. Another is Arrhenius constant. And another name, that is frequency factor. Why it is frequency factor? That we will also understand. So it has three names. That is, this is basically a constant. A is a constant and K is the rate constant. And the most important parameter we are going to understand, that is EA. EA is basically the activation energy. Activation energy is the energy that is required for starting of the reaction. Without this energy, you cannot able to proceed. The reaction cannot able to yield the product. So this is activation energy. This is activation energy, and here R is the rate constant, gas constant, and T is temperature in Kelvin square. Okay, these are all the parameters of the Arrhenius equation. And from this equation, first thing, if we increase this T then what is going to happen? This exponential term, this E, and another term, that is EA by RT. This term is called the exponential term. exponential term. This exponential term will going to be decreases, and it is, you can see the minus value. So when it is increases, this total value will decreases. So naturally this value is, that is, you can write this equation a, that is e to the power a by RT. So from this equation you can easily understand when the temperature is increased, this value will going to decrease, and if it is decreased, then this value k value will increase. So we can write higher temperature means high temperature. Here is the Kelvin scale. Absolute temperature means what? Higher rate constant. Higher rate constant. So if the rate constant is higher, then what is going to happen? The reaction rate will be increased. Second thing, that is EA. If the activation energy is decreases, then also this value will be decreases. If this value decreases, then what is going to happen? Then also the activation energy increases. Activation energy decreases. If it is increased, then K will be decreases. So if activation energy is decreases, rate constant increases. Rate constant means you can write K is increases. So this is the very, very important conclusion you can make from this reaction. Okay. Now you can see one thing. If the T value tends to infinity, then we can see the K is equal to A. This type of question may come, that when T value is infinity, then what is going to happen? Right? If the EA value, that is activation energy, is 0, then what is going to happen? Then also K is A. At that time, there is no dependence on the temperatures. So you can understand activation energy. What is going to influence the activation energy? That will be discussed in the latter part. How activation energy is important here. EA is 0, means up to K is equal to A. At that time, the reaction becomes independent of the temperature. We can write it. Reaction means rate of reaction, ROR, is independent of temperature. So we can understand this very important thing. Arrhenius equation is this, and this is the P exponential factor. This is the exponential factor, and we can understand one thing. This exponential factor is dimensionless. Why it is dimensionless? Let's see. This is joule per mole. Activation energy unit is joule per mole, and R is Kelvin. R is K. Sorry, R is आपको joule per Kelvin per mole, right? And T value is Kelvin. So you can see all those are cancelled out. So it is dimensionless. So we can put this value. So we can say the dimension of this A is basically, that is equal to the K. The value of A, you can write from this, a very important conclusion, that A when the EA by RT has no dimension, right? Has no dimension, then the dimension of the A is equal to the key. Because these have no dimension, means we can write, okay, and that is the reason, and it will change with the reaction order. If the order is first order, then it is per second. If the order is zero order, then that will be different. So dimension of these changing with the order of the reaction, and that is why it is called the frequency factor. So till now we have understood many important things from the Arrhenius equation. How do we relate with the temperature of the reaction with rate constant? Basically, temperature is increasing, means rate constant increasing, right? We understand P exponential factor. We understand the exponent of the E exponential factor, how it is dimensionless, how the EA, when EA, that is activation energy, is zero, that there is no dependency on the temperature. Temperature only can be influenced when it is having the reaction demanding some activation energy. If there is no activation energy, temperature has no use. So these are understood from this. In the next, we will understand how this Arrhenius equation can be further expanded into the different forms. Is equal to P exponential factor into the E by RT. Very simple relationship, and it will give a lot of information. Now we expand, we take the natural log on the both the sides, and we get this. Right? So we can expand, we can see how, and now if we convert this natural log into the log with the base 10, then it will be looks like this. After converting this natural log into the log, that will be, now we are dividing So now what we do, we will compare this with a straight line, and we found the curve is like this. First we ln k with temperature. First we plot this and we will find this. And here you can find there is a slope. There is a slope of there we can find the slope A by RT. Right? We are plotting by 1 by T. When we are plotting 1 by ln k by 1 by T, that what we find, there is a curve with having the negative slope, and this negative slope is equal to the EA by RT. So this is a negative slope and A by RT. Now we want to plot with respect to the log k to 1 by t. That will be also you find, but its slope is changes. Slope is changes. Here the slope will be A by R, right? Here the slope will be A by 2.303 R. Okay, this is a very important graph of this Arrhenius equation where we expand this Arrhenius equation like this. So these are all, but there is another thing left, that suppose at T1 the rate constant is K1, T2 its rate constant is K2. By putting this value in this equation, we can able to derive a relation, very important relation, that is AN K2 by K1. You can do with yourself. You can find it very easy. R, that is T2 minus T1 by T1 by T2. Now we can expand this, we can convert this natural log. It will find log of K2 by K1 is equal to A by 2.303 into R, and same thing will come here. This is a very important relationship, and this relationship that we have to utilize during solving the numericals, right? So this is how the Arrhenius relationship, Arrhenius equation looks like. I will give you a very simple question, but if you understood it properly, then you can only give this answer properly. Okay? Arrhenius reaction may be represented in these forms. May be represented. That you have to check whether that has been written correctly or not. I think that we will discuss in our next video. In the next video, we are going to discuss the activation energy, also the collision theory, and that will be the end of this chemical kinetics part, right? And you have listened to my video very patiently. That is why I am very much thankful to you. Thank you very much. Be best and have a good day.